We're good to go.
Alrighty.
Cool. So I guess I'm Luin. I'm mechanical mentor on 5985. And with me is Hayley.
Mhm.
Well, not with me, but
Hi, I'm Hayley from 3132. I mentor CAD awards, random things.
So yeah, today's presentation is on power transmission. So gears and belts and chain are my play on words with the lions and tigers and bears are my, but Wizard of Oz is probably too old now. I would hope not, but we'll see. So yeah, we're going to talk about power transmission, um, why we use it, how to use it properly. Um, yeah, well, let's get into it. So, uh, in this video, or presentation, we'll be exploring the concept of power transmission in FRC, which is the process of transferring energy from one point to another, typically from a power source like a motor to an output mechanism that performs a specific function like an arm or an intake. We often rely on motors to move our mechanisms, but sometimes you can't position the motor directly where you want to apply its power. This could be because the speed or strength of the motor alone can't achieve the desired output, or the position of the motor isn't ideal. For example, placing the motor on the end of a long arm isn't ideal because you want to reduce the weight as much as possible, and it also puts the expensive motor at risk of being hit and damaged. This is where power transmission comes into play. It allows us to effectively transfer the motor's power at the correct speed and strength to the mechanism that we want to move, while positioning the heavy and expensive motors in more ideal positions.
So, today we'll take a look at some theory that makes the transmission work, and then four main types of power transmission that you're going to see in FRC, and then go into some examples and tips and tricks for how this all can be implemented. The reason for this discussing all of these topics is to teach you how to harness the rotational force from the motors and how to power the mechanisms that you design. The first theory that we're going to look at is torque, which is this twisting force that induces rotation at a given point and is measured in Newton meters. You can find the quantity of this torque force by multiplying the force by the distance from the pivot point that the force is applied. This can also be done in reverse to find the force output from a system by dividing the known torque of your motor output by the distance that the force is being applied to the system. Now, let's take a look at the source of the torque, motors, and how to understand their documentation. Without these motors, there would be no reason really for this presentation. These terms might seem a little abstract at the moment, but bear with me. Each of them do tell you important information to help you decide what to use depending on your mechanism's priorities. This graph shows you all the values that you should roughly expect to see given that the motor is supplied with 12 volts. So the x-axis of this graph is the output speed of the motor. All the way to the right is the free speed, which is the speed at which the motor runs when it's not under any load. For example, the weight of a flywheel or anything else exerting force on the output shaft. This is the max speed of a motor. Once it's under load, the angular velocity will decrease all the way to the left, which represents speed equals 0 when the motor's not outputting any speed. And keeping in mind that this is while the motor is being powered, which then means that the only reasons it shouldn't be spinning is if it were broken or stored. The y-axis of this graph uses different units and values depending on the information that we're interested in. They use different colors or different types of lines. So make sure to reference the legend at the bottom of the graph and also read the axis labels to understand what units you're working with. Um, can you go on to the next slide? I think we accidentally left
Oh yeah,
two
there we
different
go.
versions in. Yeah, okay, thank you. So the blue line here represents the torque, which is the rotational force that we just talked about. The store torque is the max amount of torque that the motor can output at speed equals 0 on the graph and drawing its store current. We talked a little bit about the relationship between torque and speed earlier. Usually, depending on the application, you want to gear your mechanism differently. This graph confirms that relationship. The red line that you see represents a current draw, proportional to the torque. And also notice that the max current is when the motor is stalling. The yellow line represents the output power. Notice that this is a parabolic shape where the closer you get to 0 RPM or the max or free speed, the less power output you have. The green line here represents the efficiency, which is the percentage of the electrical power being converted into mechanical power. We'll talk about this from a mechanical perspective a little later, but generally there's no need to worry too much about this in FRC just because the matches are relatively short. Mostly you are trying to focus on getting the speed or torque correct.
So your motors can only output a certain maximum force, and in some cases you'll need quite a bit more force than can be squeezed out of the motor itself. We can solve this issue using the concept of mechanical advantage, which is the measure of how much a system amplifies a force. The amount of mechanical advantage a system provides can be determined by dividing the output force of the system by the input force. This example shows a block and tackle system where you're trading force for distance in order to be able to lift a heavy load, i.e. you must pull twice as much rope, but it doubles the amount of force you pull the rope with. You'll find that due to the formula for torque, most simple machines function by trading force for distance. Another way mechanical advantage can be obtained is by using levers. So Archimedes once said, "Give me a lever long enough and a fulcrum on which to place it, and I shall move the world." Longer levers provide more mechanical advantage, allowing small input forces to generate a much larger output force. When we talk about levers, there are three types or classes of levers. In a first-class lever, the pivot point or fulcrum divides the rigid beam into two arms. The arm that has the input force is called the effort arm, and the arm that has the output is called the load arm. If the effort arm is longer than the load arm, mechanical advantage is created. Inversely, if the load arm is longer than the effort arm, you have a mechanical disadvantage. So pictured here is a first-order lever, where the fulcrum is between the effort and the load, like a seesaw. Now, if we arrange a bunch of levers in a circle around the same fulcrum, hey, it's a gear. And if we analyze the forces at work, we can see that they don't look like the lever from earlier. The driving gear has the effort between the fulcrum and the load, and the driven gear has the load between the effort and the fulcrum. That's because these are third and second order levers respectively. An example of a second order lever is a wheelbarrow, and an example of a third order lever is a shovel. This same lever analogy can also be applied to pulleys and sprockets, which we'll discuss later. So these levers or teeth interact with each other and transfer torque between themselves. The teeth from the driving gear will push on the teeth from the driven gear and make it move. This reverses the direction of the input and produces mechanical advantage if the gears are different sizes. We'll go more into depth about that a little bit later. When it comes to gears, there are a whole bunch of different types that exist. They all have their own purposes, but only a selection of them appear frequently in FRC. In FRC, the most common types of gears and gear arrangements are spur gears, bevel gears, spur gears arranged in a planetary formation, and rack and pinion gears. So the most common type of gear everywhere is the spur gear. This is because it is the easiest to manufacture, making it the cheapest and most accessible option. In FRC, you'll find spur gears in almost all COTS gearboxes, and they're largely used in the majority of custom gearboxes as well that teams will design and build. As with all things that exist, spur gears have their pros and cons. They're the most efficient type of gear because they have the least contact, with only 1 to 2 teeth in contact with the next gear at any time, allowing for less energy losses to friction. However, this results in the teeth experiencing extremely high impact loading as the contact occurs suddenly and all at once. This means lower durability and higher noise and vibration. Bevel gears are also another type that we'll find in FRC, and they're the best option for when you need your output to be perpendicular to the input. In FRC, bevel gears are most commonly found in swerve modules or the 90-degree drive kits. Custom bevel gears are extremely hard to manufacture and so are only really seen as printed components in low-load applications. As well as spur gears and bevel gears, another gear type that you may hear talked about in FRC is a planetary gear. However, it's actually an arrangement of spur gears. So planetary gearboxes are prevalent in FRC as there are COTS options that allow for customizable reductions in a very compact form factor. Products like the Rev Max Planetary and the Vex Versa Planetary allow you to customize the gear ratio by stacking planetary cartridges together to form a large reduction without the need for large custom gearboxes. Planetary gearboxes get their name because they look like a planetary system, where the planet gears rotate around the central sun gear. They work because as the sun gear is rotated, it spins the planet gears, which in turn spin the ring gear. If the ring gear is stationary and the planets are connected through a carrier plate, then the carrier plate will rotate instead. This is the basis behind how the cartridge-based planetary gearbox works. Each cartridge contains a specific reduction and has an input via the sun gear and an output via the carrier plate. Stacking these will result in a higher reduction up to a maximum reduction based on the load rating specified by the manufacturer. To best avoid exceeding the load ratings of the gears, make sure that the highest reduction cartridge is closest to the motor. So you'll see in this Rev Max Planetary, it has a 5-to-1 closest to the motor. In FRC, it's uncommon to see a straight rack and pinion being used, although more and more these days. However, sector gears, which are effectively curved racks, are becoming much more prevalent, being used on articulating shooter hoods to change the exit angle of the game piece, and increasingly as compact solutions to pivot things like arms and especially shooters in this 2024 season. In FRC, most of the gears you'll encounter are 20 DP or 32 DP gears. This refers to their diametral pitch, which is how many teeth are in an inch of circumference, which at the end of the day is just how close together the teeth are. 32 DP gears are really only useful for reducing backlash. The available sizes are also pretty limited compared to 20 DP, and they can't handle as much torque. This makes them usually acceptable for the first stage of a reduction, but not ideal beyond that. A gear's pitch diameter, in inches, can be calculated by dividing the number of teeth by the diametral pitch of the gear. For example, a 20 DP gear with 24 teeth has a pitch diameter of 1.2 inches. Another thing that we have to do with gears is grease them. So we can either grease them with dry grease or white lithium grease while spinning them by hand. You usually don't want to run dry gears due to the high friction involved, and you can experience some wear. Most teams will use white lithium, but the idea behind using dry grease is to not build up dust and metal shavings, which result in wear and tear. Another thing you can do with gears is use an idler gear. So idler gears are gears that you put between the input and output. These help with the spacing and rotation, but they don't affect the resulting ratio. For gears to work efficiently and undergo the least amount of wear, they must be located a precise distance from each other. If they're too close, the teeth rub, increasing friction, decreasing the efficiency, and increasing wear. In some cases, it'll cause the gears to jam up entirely. On the other hand, if they're too far apart, the area of contact between teeth is too small, and so the load is distributed over a smaller area. This increases the pressure on the tooth and can cause it to break off. The best area for the teeth to contact is at the pitch diameter, which can usually be found on a gear's spec sheet. The average of the two pitch diameters is how we find the ideal center distance between two gears. Additionally, if the gears are not correctly aligned on the shaft and there isn't full tooth contact between the gears, this will also cause the teeth to experience an increased amount of force and break the tooth. So how can we quickly and easily calculate the center distance of two gears? So the tool that I like to use is the West Coast Products Gear Center Distance Calculator. You can input the diametral pitch of the gears being used in step 1. In step 2, you put the number of teeth of each of the gears. And then step 3 will output the gear center, which is the ideal center distance between your two gears. This extra center value here of 0.003 inches is pretty standard and is added onto the calculation mostly to account for machining tolerances of the gears and to make sure that, yeah, they're the right center distance apart.
So gears are great for short distances, but if you need power transmitted along a further distance, having a lot of gears can get really heavy really quickly. Chain can help with this because it is a little bit lighter over longer distances than gears would be. Chain works by driving the sprocket with a motor, and then the sprocket transfers the torque into the chain through the pins on each link. If you think of a chain kind of like a flexible ladder, the sprocket pulls on each rung of the ladder, moving it along. The next tooth on the sprocket then grabs the next rung and then moves the chain down again. The chain then pulls on the teeth of the sprocket that's being driven, causing it to rotate. and thus transferring the power from the input to the output sprocket. There's two main types of chain that are used in FRC. There's number 25 and number 35 chain, depending on how large each link is. Number 25 is lighter, but it will stretch under lighter loads compared to the 35 chain, which is super heavy but also super strong. The anatomy of a chain can be a little bit confusing, so we'll quickly cover what you need to know. A length of chain is made up of inner and outer links that connect together with the pins to form a loop. The inner link can only connect to an outer link and vice versa. But there is also a special component called a master link that substitutes an outer link and acts as a quick disconnect point for the chain loop. When you change the length of a chain run, you have to remove an even number of links, one inner and one outer, so you can rejoin the chain back in a loop, which also means that you can only have an even number of links in a chain loop. Now, this is where it gets confusing because you can also buy a component called a half link, which is the size of a single link with the end of an outer link on one side and the end of an inner link on the other, which then lets you create a loop of chain with an odd number of links. So how do we actually make chain the correct length for our application? Well, to do this, you use this tool here called a chain breaker. The whole idea of this is that it pushes out the pins between the links to disconnect them from the chain loop. And then once you've broken the chain, it's also best practice to put it together with a master link for the reasons we talked about in the last slide. Let's watch this quick video from West Coast Products that demonstrates the chain breaking process.
How to break chain using the WCP chain breaker. First, place the chain with the link you want to break under the pin screw. Secure the chain in place by tightening the cup screw. Now tighten the pin screw until it reaches the hard stop. Then loosen both top screws to release the chain and separate it by pulling it apart. Repeat this process to get the chain length desired. To connect the chain, force both ends together. Place the chain with the loose pin under the cup screw and lightly tighten the pin screw to secure the chain in place. Tighten the cup screw until it reaches the hard stop. Then loosen both top screws to release the chain. Individual breakers and spare pin sets are available to order separately. How to break chain.
All right, so now that we know how to break the chain and make it longer or shorter, how do we actually know what the right length is? Well, here's a different calculator that we like to use for chain calculations. Just because the West Coast Products page, I don't think actually has a chain calculator.
I think it's not.
Yeah. So this is the recalc calculator. We can use it by first selecting the size of the chain that you plan to use, and then entering the desired center, which is the distance from the center point of the two sprockets. And then you input the number of teeth on each sprocket, and it will output you the number of links and ideal center distance for your design. The table on the right will give you some places that you can source the sprockets from, as well as the available bores that they have. Okay, so where there is a low load application that requires power transfer over a long distance, belts are generally preferred over chain because they are extremely lightweight in comparison. When it comes to transferring torque, belts and pulleys operate very similar to chain. However, the teeth are on the belt and the pulley has grooves that the teeth mesh with. While the belts are easy to use, they are only suitable for relatively low load applications as they can stretch and snap under larger loads. As the name suggests, double-sided belts have teeth on both sides. That's the image in the top right. This allows for torque transmission to multiple axles that rotate in opposite directions like those in a shooter. Belts are very flexible, which then can also lead to some cool use cases that we will demonstrate a little later. Now, In FRC, the belts that you will most commonly encounter are either GT2, which is 3 mil pitch, or HTD, which has a 5 mil pitch. As with gears, the pitch is the distance between each of the teeth. They usually also come in different widths. Most commonly are 9 mil and 15 mil. The larger width do allow for more torque because there is more area for the force to be shed across. Unlike chain though, belts come in set sizes, and so you have to make sure that the center distance between the two pulleys is precise or properly tension the system via other means. On each belt, there will be a series of numbers which can be used to identify the pitch, width, and size of the belt. So in this example, the belt on this slide here is labeled as 600-5M, 600, 5M, and 15. The 600 is telling you that the belt's length is 600 mils. The 5M tells you that the pitch is 5 mils, and the 15 is telling you that the width of the belt is 15 millimeters. So some of you might be looking at this and thinking, okay, but how many teeth does the belt really have? Well, you find that by looking at the length of the belt, which is also the circumference, and the pitch being the distance between the teeth. You can look at those two numbers and calculate the number of teeth on the belt. In this case, 600 divided by 5 gives you 120 teeth. So, how do we calculate the correct center distance? Well, we go back to the WCP website. They have a great calculator there, which operates very similarly to the one that you saw before. In step 1, you select the pitch of the belt that you're using and the unit of measurement that you like to work with. Step 2, you enter the size of each of the pulleys that you want to use. And then step 3, you put in the desired center, which is how far apart you want the two things that you're transmitting power between to be. Then the calculator will spit out 3 different belt options with the center distance closest to what you want. Usually you can just take that middle one, but the other 2 also show you the other options that you can use. So, but also when designing with the tool, we have found that the belt is still a little loose. So that's where you can add in the extra center. Usually 0.05 mil is pretty good.
So sometimes there are applications where you don't want to use either a chain or a belt. In these cases, we can look to polycord or polybelt. These are elastic cords or belts that can be made into any size loop by cutting the cord or belt to size and melting the ends together. The biggest upside to polycord or polybelt is that because it is elastic, tensioning it is very easy. Some applications in FRC are using polycord instead of a toothed belt to drive an intake or conveyor system. This means that if there's a jam, the polycord slips instead of damaging the game piece. You can also use polybelt instead of having many rows of compliant wheels, in a similar way to how it's lighter to use a belt instead of many rows of gears to transfer power over a longer distance. Using polybelt instead of regular belts to convey the game pieces through your robot is also one way to use it, because polybelt itself is wider and grippier than a regular toothed belt. Also, the flanges on toothed pulleys tend to rub on game pieces and can damage them. So now that we have an understanding of some of the applications for polycord and polybelt, how do we actually make a loop that we can use? So to make a length of polycord or polybelt, you should cut it approximately 5% shorter than the desired ideal length that's in your CAD. Then melt it together, preferably using a jig to help align the melted ends. And then lastly, sand the excess material to make a clean join. This last step is optional, but it's recommended to prevent defects from damaging game pieces or getting snagged somewhere unexpectedly in your system. Here's a video example from Wild Stang Robotics program, so FRC teams 111 and 112, on how they join their polybelt together. So you can see they've held the polybelt in place pretty well using 2 aluminium tubes and 2 bits of angle. They then heat it up with a blowtorch and then squeeze the 2 tubes together and wait for it to fuse. Then once it's been held in there long enough, they cool the whole thing down. And then you can undo these bolts here and just slide the poly belt length out this way. So once you have your length of polycord or poly belt, you're ready to stretch it over the pulley and drive it. But what exactly does a pulley for each of these look like? So to transmit the rotational power from the motor to the system you're powering, polycord requires a traditional toothless pulley, just like in a block and tackle. Polybelt, however, requires a crowned pulley. So crown pulleys are used because it prevents the poly belt from bunching up or wandering off of the desired path and falling off the pulley. At a glance, this seems extremely unintuitive, but if you break it down, it actually makes a lot of sense. So we'll watch a short clip from this video by Steve Mould to find out why it does work.
And the description. To understand why the crowned pulley behaves the way it does, consider what happens to a rubber band when you stretch it, but only holding on to one edge. You'll notice that the band arches. This part ends up higher than it was before, and you have a curve here and here. You can see on the crowned pulley that this edge is more stretched than this edge, so we should expect the rubber band to curve upwards here. It's very subtle because the difference in stretch between
Whoops.
And the description. To understand that this edge is more stretched than this edge, so we should expect the rubber band to curve upwards here. It's very subtle because the difference in stretch between the two edges is quite small in this case, but it is there. Because of that upward curve of the rubber band, when you turn the crown pulley, it comes into contact with a piece of rubber band that is higher than the rubber band that's already on the pulley, and so it slowly shifts upwards. And the description.
So now that we have a thorough understanding of each of the primary methods of power transmission, we can compare them more closely.
Just before we go into this slide, we had a question in the chat asking when we would use a double-sided belt. Actually, Luin, can you play the video I just sent you?
Yep, the one that jumped up before.
Yeah. That's an example there of a team using a double-sided belt, but it's generally when you want to reverse the direction of pulleys in a row, or just when you have a really long run of pulleys. I don't know. Luin, do you have any other examples?
So in lots of ones on shooters this year, because you wanted to have your shooters running in opposite directions, but sometimes powered by the same motor. And so you'd use a double-sided belt that would run over the top of one and then the back of the other, and they'd spin in opposite directions. But yeah, there were a lot of double-sided belts used this year in intakes and the like. And yeah, as you can see here, you've got these all rolling. Wait, this rolls. This roller and this roller roll in two different directions. And then this one rolls in the same direction as this. Yeah, so this one and this one roll in opposite directions, meaning something goes in or out of here. And then this one, this must be like to guide it into the amp. Let's see if they show any. They don't give much context.
But yeah,
this
usually
is
intakes or shooters.
Mechanical advantage. Yeah. This brought it into their system, and they had another part that this fed it through, and depending on which way this roller spun, it either fed it through into the shooter or fed it out through this gap into the amp or trap mechanism that they had, I believe.
Oh, okie dokie.
Yeah.
Thank you for that. So here's a comparison chart that we made to help identify what method to use given your mechanism's needs. So looking at this, let's go through each one really quickly. Gears are best used in high load applications. They can provide very precise control due to having minimal slip. They can be used anywhere within a robot, provided that the reduction occurs over a small distance. Chain and sprocket are also best used in high-load applications. They can be used over a longer distance than gears, and you can usually see them in arms, elevators, and drivetrains due to their ability to provide high torque over a long distance. Belts and pulleys are best suited for low-load applications. They can also span large distances, and their flexibility lets you use them to follow some wacky paths, especially with double-sided belts. They can be used anywhere there are lower load applications, but usually it's where weight saving makes sense. Polycord and polybelt are usually used for driving intakes and conveyors to allow some slip in the system to prevent damage to game pieces. Polybelt is usually used for conveying game pieces over a large distance where using lots of rollers doesn't make sense due to the increased weight. It's also worth noting that the chain and sprocket and polycord and polybelt don't require you to have an extensively varied stock inventory to use because you can customize the length of them pretty easily. But you do need to stock a lot of polycord and polybelt if you are using them, just because they do snap through use a lot. You can also use any of these methods in conjunction with one another. For example, if you have an arm or an elevator that requires a bit of torque, you can use gears to give you a really high load compact reduction and then use chain to output that torque at a location that's further away. This just eliminates the need to use a big sprocket. So now that we've compared each of these power transmission types, there are some things that we need to talk about to just keep in mind when implementing them into our designs. The first thing is efficiency, which is defined as the percentage of input power that is then converted into output power. Maximizing this is crucial for optimizing your robot performance. So to maximize this, you have to minimize your inefficiencies or losses in the system. One of the biggest causes for inefficiency is increased friction and resistance. So to combat this, you should, one, grease your gears regularly. Make sure to grease your gears first before running them and then check them regularly before you do any testing and before a match. Add it to your pre and post match checklist. And also keeping them well lubricated just reduces friction, which also reduces energy loss. You want to also be avoiding gritty bearings. This is the same concept as the gears. We just want to be reducing friction as much as possible. When installing bearings, just give them a quick spin with your hand. If they spin freely with a smooth, continuous motion, they're good to use. Avoid bearings with grinding noises or if they catch when you're spinning. Bad bearings can be used in prototyping, but that's where they should stay. Another way that your system could be inefficient is when chain and belts skip. When they skip, there's no power being transmitted. To prevent this, make sure that they are properly tensioned. Make sure that you've calculated the center distances correctly, and also just be checking them over time, because over time they do need to be maintained and may need to be retensioned. To deal with this though, you can also be designing tensioning capability into your systems, which we will talk about in the next couple of slides.
So as previously mentioned, having proper tension reduces losses in your systems by preventing your chains and belts from skipping and stretching. In some cases, you can't achieve the exact center distance required for your design due to machining tolerances or the fact that there's something in the way. This can leave your belts and chain too tight, but more often than not, too loose. As you can probably tell, tensioning doesn't really apply to gears as they're harder to adjust and require exact center distances to work efficiently. There are three primary ways to tension your power transmission system. You can change the length of the chain or belt itself, you can increase the center distance between the two pulleys or sprockets, and you can increase the path that the belt or the chain takes. Think about how running along the diameter of a circle to get to the other side is a shorter distance than running along the circumference. So the first and most common method is achieved by changing the distance the chain has to travel. You can implement idling sprockets into your design that force the chain or belt around them to increase the path of the loop. It's best to design some adjustability into these to allow for if your chain or belt stretch. On the left here, we have a sprocket with a bearing that's mounted on a bolt. This bolt can be loosened and moved along this slot and then tightened back up to lock it in place, allowing for adjustment if needed. In the center, we have an adjustable idler pulley for a belt. It consists of a pair of flanged bearings that are free to spin on a bolt, which can then be adjusted up and down using this other bolt to tighten it up. As the bolt tightens, the bearing is pushed down onto the belt, increasing the path the belt takes and increasing the tension. On the right is one of 254's designs from 2019, and in this case, an idler pulley is used to both tension the belt and to reroute it to fit the shape of the mechanism. These are all very clean and easy to implement solutions. However, there's another tensioning method using the same technique that should be avoided. Floating sprockets. You'll see them being recommended or even used in some cases, but I'd very much avoid them if you can, especially in high-speed applications. This is because floating sprockets have a risk of popping out of the chain loop, creating a hazard to both you and if it exits the robot. Creating a hazard to both you if it exits the robot and the robot itself, as the sprocket is now free to fly, potentially damaging your mechanisms or, more commonly, your wiring and electronics. Also, as torque is applied in each direction, the floating sprocket tends to move perpendicular to the direction of the chain, so in this case, up and down, leading to less efficiency and clearance being required on either side of the chain for it to move into. This method should only be used as a last resort, like if something goes horribly wrong and you need to fix it before you get to your next match. Sometimes you don't have the option to mount something on the robot in the path of your belt or chain, and while the aforementioned floating sprocket addresses that issue, there are much better ways to do this. Clamps can be used to increase the path of a system by curving the chain or belt inwards, increasing the path length, and therefore increasing the tension. On the left, you can see a clamp that uses a block held in position by aluminium plates to change the path of the chain. A major downside of this style of tensioner is although it's made from a low coefficient of friction plastic like Delrin or nylon, it greatly increases the system's friction, which decreases its efficiency. The chain will also quickly wear away at the plastic, requiring constant monitoring and regular replacement. Although increasing the footprint of the tensioner, it would be possible to design a clamp-style tensioner for chain that uses bearings and sprockets to reduce the friction and wear. On the right, we have a very crude clamp made by zip tying two bearings together, one on either side of the belt. This pulls the belt in and around the bearings, increasing the path taken, therefore increasing the tension. It's labeled as a prototyping method because while it works, it's not ideal to use on a final robot, as the bearings may slip off the belt and the belt tension will then be lost. As with the chain clamp, it would be possible to design a much more suitable and robust belt clamp for your competition robot if required. You may come across situations where you find there's no space to mount an idler tensioner, but chain loop or belt has a portion of it that doesn't contact the sprocket or pulley, so a section that doesn't continuously rotate. In these cases, you can use an inline tensioner. This uses the second method of tensioning where you make the effective length of the chain loop or belt shorter. For a belt, this involves clamping down on two parts of the belt and pulling them together by tightening a bolt. It bunches the belt up in between the two halves of the tensioner, increasing the tension. For a chain, an inline tensioner replaces a section of the chain itself. You can then turn the screws to increase or decrease the distance between the two ends of the chain, making the chain loop longer or shorter to meet your needs. These inline tensioners are really only viable for systems that are non-continuous. This means that through the full range of motion of the system, there's a portion of the chain or belt that doesn't contact a sprocket or pulley. This is because inline tensioners cannot mesh with them and will jam up the system, potentially damaging your sprocket or pulley. The third main method used to tension a system is by increasing or decreasing the center distance of the sprockets or pulleys. To do this, you need to look at ways of moving their mounting points or the axle that they're on. So on the left here, we have a bearing block that clamps onto a tube. Its position can then be adjusted by loosening the bolts here and here, and then turning the cam, which moves the block back and forth, increasing or decreasing the center distance of the system. The clamping bolts can then be tightened again to lock the block in place. In the middle, we have a similar concept. However, a bolt is being used to decrease or increase the center distance. On the right, we have an adjustable motor mount. It can be adjusted by loosening the bolts and then sliding the motor up and down the slots, thereby increasing or decreasing the center distance of the system. When you have a motor in a location with appropriate tension, the mounting bolts can be tightened again and to lock it in position. This method can also be applied to the driven side of a system, similar to the clamping block, but without the cam or the bolt. These styles of tensioner also allow you to more easily assemble the chain or belt system. This is because the components can be installed, and then the system can be tensioned afterwards by increasing the center distance of the two sprockets or pulleys. Now we'll move on to talk about the primary reason you would want to transmit power, rather than direct drive a system with a motor: ratios.
So, although relatively simple, ratios are one of the most important topics when it comes to this power transmission. This is because more often than not, you want your output to be faster or stronger than your input, and this is done using ratios. In these examples, we're going to be using gears, but the same theory here can be applied to any of the topics that we covered before. So, ratios are found by dividing the number of teeth on the driving gear by the number of teeth on the driven gear. When analyzing a gear pair, driving gear is the input and the driven gear is the output of the system. On the left, we have our higher ratios, which results in higher speed, lower torque. And on the right are the lower ratios or higher reductions, which result in lower speed but higher torque. So let's take a look at the gears on the left. A big gear driving a smaller gear gives us an increase in speed and a decrease in torque. This increase in speed occurs because for every one rotation of this big gear here, the smaller gear rotates 3 times. So for example, if it's rotating at 100 RPM or revolutions per minute, then the green gear is going to rotate at 300 RPM. When it comes to the decrease in torque, we can think back to how gears are essentially just a bunch of spinning levers. When you're analyzing where that energy goes, we look at the formula for work, where work is equals to force times displacement. This means that for the same amount of work, if there's a larger displacement, e.g. 3 rotations instead of 1, then there is a decrease in force. What if we wanted to get more torque output though? We would then need to have a smaller gear driving a larger gear. So in this example, you have a 36 to 60 reduction, which also just means that for every 5 rotations of the orange gear, the green gear is going to spin 3 times. How does this apply to the mechanisms that will be on our robots? Well, shooters need to prioritize speed because you're often shooting long distance where you need to impart high velocity to your game piece. Intakes also prioritize speed, but to a slightly lesser degree, because they do need to run at a higher speed than the drivetrain to pick up game pieces quickly while the robot travels around the field. That being said, they also do need to get game pieces into the robot, and some gears do require more torque than to do that or to maintain a hold onto your game piece. Elevators generally do require more torque, but still need speed because they operate multiple times in the match to score, and you want to decrease your cycle time as much as possible. And climbers usually require the most torque, where similarly to an elevator, they need to be lifting weight, but they do need to lift the weight of an entire robot with bumpers and batteries, or in some cases, like in the photo that we have here, multiple robots. When it comes to drivetrains though, torque is important for pushing power if there's defense, otherwise you're probably prioritizing speed to decrease your cycle time.
So 3D printing is an exceptionally useful tool for power transmission. It allows you to print components so that you don't have to purchase them, which significantly reduces lead time and part cost, especially for us Australian teams. With 3D printing, you're able to print gears as well as pulleys for both belts, polycord, and polybelt. You should not print sprockets, as chain is usually used in high-load applications that printed parts are just not suited for. When printing power transmission components, you must be sure to design your parts correctly and print your parts out of the right materials and with the right settings. So first, let's talk about the most common filament materials used in 3D printing. So ABS is a readily available filament commonly used in 3D printing that has quite a good strength to weight ratio. However, when you print it, it off-gases some pretty bad fumes, and it can be difficult to print as it's prone to warping. Because of this, I wouldn't recommend its use, as there are better materials that are easier and safer to print. PLA is probably the cheapest and easiest to print material on the list, making it the most used filament in FRC. It's strong, but also really stiff, which makes it brittle, meaning that it has a low impact resistance. PLA is also has a relatively low melting point, potentially causing it to warp and degrade at only 50 degrees. PETG is another common material in FRC. It has a lower stiffness than PLA and also a much higher melting point. This makes it much more durable material. In one test, it outlasted PLA and ABS gears by 22 and 37% respectively. This is the filament that we use the most on our robot, 5985, and we haven't really had many problems with it. Nylon is probably the best material to use when printing power transmission components. It's as strong as PLA without the stiffness, which means it's less brittle, as well as having a higher temperature resistance. It also naturally has a lower coefficient of friction compared to other filaments, making for a more efficient system. The downside of nylon is that it's more expensive than the other materials, and it can also be harder to print. So before we delve into the specific design of parts, there are a few things to keep in mind when 3D printing power transmission components. 3D printed bores are not that strong and are prone to rounding out, just like the hex head on a bolt. This then allows the shaft to free spin inside the printed part, preventing power from being transmitted. To stop this from happening, you can use a hex bore insert, like these ones pictured here. I'm lost, sorry. These inserts also exist for motor-specific splines, like the Falcon and pictured here, the Kraken. These are aluminium parts that you can press into your prints so that they don't round out. The key to prevent parts from breaking is to spread the force over as much area as you can to reduce the stress experienced by the part. For pulleys, try using a 15mm wide belt where possible, and for gears, use a 10-tooth DP profile, as it makes each tooth larger, as well as trying to make your gear as wide as you can to spread the force out even more. Another thing you'll need to remember is shrinkage, because 3D printed parts are produced by using melted plastic. As the plastic cools down, it shrinks, meaning that your holes become smaller. To fix this, I generally add 0.3mm to my dimensions to combat the shrinkage. And last but not least, when printing components that are going next to a bearing, you want to add a 1mm boss against the inner race for the bearing to prevent rubbing. This is because in a bearing, either the inner race or the outer race rotate. And so if your printed part is touching both of them, there'll be a large amount of friction created, which can also cause wear on the printed part. So over on the right here is a pulley straight off of our intake from this year. And you can see that somebody forgot to put in the 1mm spacer, which then had the outer race of the bearing rubbing on our part, just kind of degrading it a little bit and causing some damage. We'll come back to gears later because there's a lot to discuss, but for now we'll talk about pulleys. So when printing pulleys, you might be tempted to download the step file of a COTS part and just print that. But the design for the metal COTS pulleys has a very thin flange that's prone to breaking, and it also has a cavity which creates overhangs, making it harder and slower to print. There can sometimes be text in the model as well, which also unnecessarily increases your print time. To fix these issues, it's best to generate a pulley in your CAD software of choice. For example, in Onshape, you can import configurable pulleys using the MKCAD app. You could also modify the step file of the COTS pulley to remove the cavity and add a thicker flange, but it can be a time-consuming process. On the right here is I believe, 42-tooth pulley that we used on our robot this year. It was printed out of PETG and has a recess for the 8mm spline XS insert, so that it can be attached to the Kraken X60 motor. The flanges are 4mm thick and chamfered on the inside to help guide the belt into place. Although we are using a 9mm wide belt, the gap for the belt is 10mm wide to allow for slight misalignment if it occurs. Now that we've covered tooth pulleys, we'll discuss polybelt and polycolored pulleys. So for polybelt, you can download and print the file straight from AndyMark or another COTS vendor. There are no features that make the printed version any weaker than the actual COTS version. For Polycod, however, you might want a different size to what's available, and you can very, very quickly design a pulley in your CAD software by sketching its profile, allowing offsets for clearances, sketching the body of the pulley, make sure it's only the top half. Then you can revolve the pulley around the center line, put your bore in, remember to add your offset. And yeah, that's it right there. So with our bore, we don't need to worry about using the 3D printed inserts because Polycord is unable to transfer high enough torques anyway. You can also make pulleys for 2 or more polycords, so you just add another profile next to it, so you can power multiple things off of one axle. So now we're going to go on to gears. So when it comes to gears, you might remember that we talked primarily about spur gears. Whilst they're the most efficient type of gear, they're not the best. They're great for metal gears, but when making them out of plastic, we want to minimize the tooth pressure to avoid breaking the teeth off. So to reduce the amount of pressure on each tooth, we can use a helical gear. So helical gears have teeth that are slanted at an angle, commonly somewhere between 15 and 25 degrees, and that's the helix angle. Because of this, the meshing of the teeth occur gradually instead of all at once like with the spur gear, and there are more than one tooth, usually 2 or 3, in contact at the same time, which distributes the load more evenly between them. This means that helical gears can be used at higher speeds, have a higher load carrying capacity, experience less wear, and are often smoother and quieter than spur gears. However, there is one downside to helical gears. Because of the slanted teeth, axial forces are introduced when the gears mesh. As you can see in the GIF on the left, this force wants to slide the gears away from each other on the shaft. The direction the gears are spinning changes the direction the force is acting, and the magnitude of the force increases as the helix angle of the gear increases, as shown in the picture on the right. However, there's a way to get all of the pros of the helical gear without the cons. And that's by using a herringbone gear. So a herringbone gear is essentially just 2 helical gears next to each other, but in one part. This means it gains all the benefits of the helical, but without the drawback of the axial forces. So why don't we see these herringbone gears absolutely everywhere? It's because the slanted teeth connect at a single point, which makes them extremely hard to manufacture using traditional techniques. However, this makes them perfect for 3D printing. They can be very, very easily manufactured using any additive manufacturing technique. So we should use them for pretty much every low load gear application in FRC to lighten up all of our robots. When using a herringbone gear, the most common parameters are to have them be 10 dp, wide, and as low of a helix angle as possible. But as with most things, there's a downside to herringbone gears. Because of the shape of the teeth, you can't just slide them into place to mesh them. You have to mesh the gears together before installing them, which makes it harder to install. This does mean that they're self-locating, which has some pretty cool applications, like in this turret here. The middle ring is actually located just by all of these herringbone gears around the outside. Now that we know what to design, how do we actually print it? So for power transmission components, we want them to be as strong as possible. When it comes to slicing your parts, the most important thing to do is to increase the number of walls. This makes sure that your teeth have 100% infill no matter what your infill percentage is set to. And you should always keep your infill percentage above 35% to ensure that there's enough material to properly transmit the torque from the bore out to the teeth without anything breaking. For the lower infill percentages, you can add small slits in your design to force the slicer to add walls in that area. This makes for added strength in your print. So we have a pulley here and a gear here. A pulley on the right, gear on the left. These can also be used in conjunction with the inserts for having the best torque transfer.
Alrighty, now let's talk about how to package everything, which is essentially how your robot components, including motors, electronics, gears, belts, and chains, are positioned within the space that you have available. There are 4 important things that we'll be talking about today. These are 1, how the components affect your robot's center of gravity, which you want to keep low and centered for stability when you're driving. 2, whether the components will be on a moving mechanism. 3, what parts of the robot will be exposed to collisions and field elements. And lastly, accessibility, which is just how easy it is to access the system when you need to maintain it. Center of gravity, or COG, is defined as the average location of the weight of a robot. Typically, you want your robot's center of gravity centered in the X and Y planes, meaning left, right, and front, back, and as low as possible in the Z axis or the vertical. This keeps your robot stable and it stops you from tipping, especially when you're playing a high contact game where the robot experiences great acceleration in collisions. You want to position your heavier components like your drive gearboxes, climbing mechanisms, elevators, arms, and all that low and close to the center of your robot. When designing mechanisms that move or deploy, like an intake or an arm, you have to consider how they affect your center of gravity. For example, moving an arm is going to shift your robot's COG, affecting its balance, and you want to factor these shifts into your design to maintain stability during gameplay. You can minimize that shift by reducing the weight of your moving components. The lighter the part that needs to move, the more efficient your system also becomes. Taking an intake, for example, you don't want to pivot a heavy motor on the end of your intake, so you can consider using smaller motors or use what we just learned about power transmission to instead use belts to mount the motors closer to the pivot while still being able to power your rollers that are on the end of the intake. Doing this also lowers the load on the mechanism, allowing you to use smaller motors, or in this case, smaller pistons for the pivot. Minimizing the weight also allows you to use up less of the power budget. So the picture on the right here is a 2018 game. It's an ARM design for the 2018 game, which needs to lift milk crates up in the air. So recall our lever examples from before. When you're designing a mechanism on the end of an arm, we need to carefully consider what we're using and where they are positioned. Further away from the pivot that the mass is, the force to move it increases dramatically. So to combat this, you need to either increase the robot weight by adding another motor to have the available power, or you need to increase the reduction, which then decreases the speed that the arm can be moved at. And in FRC, lowering your cycle time is a top priority. So you really don't want to decrease the speed if possible. When you're designing an FRC robot, you also need to consider how moving parts interact with other systems. You need to make sure that nothing gets in the way of your other mechanisms during the match, and this is especially important for intakes, arms, and climbers that frequently move in and out of the robot's frame perimeter. During matches, the robot's inevitably going to be exposed to external hazards such as field elements or collisions with other robots. Think about how exposed your critical components, like your motors, power transmission, electronics, are during gameplay. Any parts that stick out of your robot could be vulnerable to damage. Even elements that within your frame perimeter but exposed might get snagged on external things. For example, this unfortunate intake on the left here, or the exploded air tank to the right. Consider guarding these by either putting power transmission on the insides of your intake plates or putting a plastic removable shield over any of the vulnerable components. One method that was common a few years ago was chain and tube drivetrains, which was great for protecting the chain from the field and carpet, but was a nightmare to maintain. Which brings us to the next point, accessibility. Always consider how easy it is to access components of your design for maintenance. During competition, quick repairs are often necessary. If you need to remove multiple layers of mechanisms and parts just to fix a belt or adjust a chain, you're going to lose valuable time or even miss a match. Plan ahead to ensure that the parts that need frequent adjustments, like your belts, chain, or even gears, are easily accessible. Components like polybelt, for example, might require regular tensioning or even remaking and reassembling onto your robot. By designing these with access points, you can then make it easier to address issues without disassembling major parts of your robot in the pit. Yeah, and Mel and I probably have PTSD from, I think, 2018 when we needed to redo one side of our drivetrain entirely when we had back-to-back matches. That was great. Yeah.
God, in 2018 we had to redo drivetrain gearboxes as well.
Oh no. Well, on the topic of gearboxes.
Wait, this is actually the gearbox that we had to replace. Oh God. So gearboxes are used to implement gear ratios, and they can also be used to couple motors together so you can put more power into the output. So your ratios, your input and output gears are different sizes, and for coupling, you've got more than one gear or pulley and sprocket on the shaft. So on the left here, we have the West Coast Products SS gearbox. So this was a funky little gearbox where you could actually have different ratios by adjusting the mounting position of these motors. There were two holes that were pretty much right next to each other, and for one gear ratio, you use the hole on the left, and the other you use the hole on the right. What I was talking about replacing the whole gearbox was somebody had used the wrong hole, and so the two gears were ever so slightly too far apart, which increased the loading on each of the teeth, and broke the teeth in our drivetrain gearbox. That was not fun. And on the right here, we have another example from 254 in 2019. We have a really compact gearbox with two motors that powers their arm that move lifted up and down that year. We have here an example of belts and pulleys. So this is 1678's 2022 robot. It's a very, very nice use of belts. They wanted all of their motors to be down low to lower their center of gravity, which left a very large distance between where they were actually shooting from and where their motors were that were powering their shooter. And because of this, they used a belt because it was the lightest available method. They also built in a tensioner, which uses the method we discussed with the bolt that pulls on the belt to increase the length. And they have two motors attached to the same belt. And then here we have some polycord and polybelt examples, a hopper from 254's 2017 robot, or the prototype at least, 118's 2012 intake, and then 125's 2017 intake. Using polycord here, you can see it can go around corners. Polybelt is just wider and flatter. And can you imagine how much heavier it would be to have like 5 rollers in here instead of all of these belts? And then last little bit is some food for thought. So we've talked a lot about rotary motion, but how can we actually turn that into linear motion? Here you can see the inline tensioner that we were talking about earlier, but by pinning the carriage of this elevator onto the chain, as this sprocket rotates, this side of the chain moves up, this side moves down, and when this side moves up, this carriage is attached to the chain, and so the carriage goes up. So that's how you can get it out of an elevator. We have this funky little device from Argos, which has a sprocket meshing with the tube instead of a chain, kind of like a rack and pinion. Very, very cool. And then last one, we have an actual rack and pinion. We have the teeth 10 DP gears here and the teeth on the polycarbonate rack. And this was their 254's intake in 2023 for picking up the cubes.
And last slide. We'll go over an example calculation really quickly. So when designing intakes, you want 2 times the drive speed for your intake service speed. We'll go into details on why this is the case in the intake presentation next week, but it essentially allows you to pick up balls instead of driving over them or letting them roll away. In this example here, we're going to assume 12 feet per second drive speed, and which then means that the intake surface speed needs to be 24 feet per second. All right. So this is the recalc intake calculator. First, it's a little bit spread all over the place, but put in the information about the motor that you want to use, and then the roller diameter, and then the drivetrain speed. So all of the red boxes there. This is then going to give you the recommended reduction over at the very bottom, which is the ratio that you want to use. If you want to double check that, do the step 2 boxes, put in the fill out the ratio box with the reduction that is recommended there. And on the right there, you'll see that the linear speed is actually what we just talked about. So with this 2.14 ratio, I would then probably look for belts and pulleys that you have that make up a reduction of 2. So for example, from West Coast Products, you can just get a 12-tooth motor pinion and a 24-tooth pulley, which then gives you a 1:2 ratio. Pretty straightforward. Yeah, and that's just about it for our presentation. Let's open it up for questions.
Yeah. If you guys have any
Right,
questions, feel free to.
Thanks very much, Hayley and Luin, for presenting tonight. We'll go over to questions in a second. I'll stop the recording for that bit. Just before we do that, and I let everyone disappear off the call, I will just plug our next couple of presentations over the next few weeks. So next week, Luin and Hayley are back talking in more detail about intake design. The week after that, we've got Zach from Project Bucephalus and also from the Unqualified Quackers talking about sensors and control systems. 25th of November, we're hearing from DeWood from EMUs about team sustainability. On the 2nd of December, we've got a talk on practical inclusivity from the folks at Project Bucephalus. That one will have a later start time of 7:30. And then the last one on the 9th of December is about strategy, and that's from VATS on 3132. So hope to see you on some future sessions as well. Thanks for joining us. Thanks again to the presenters, and I'll stop the recording now and we can go over to question time.